Hello, I'm back for your second week or your second lecture about whole farm planning, and today is going to be about linear programming from beginning to end. So I hate to tell you, I was excited yesterday in one of the small groups. One of your classmates, Marco, I'm sure many of you know him, was sharing his computer screen that had Microsoft OneNote, has a fantastic way that you can graph and solve these problems. And I have OneNote. But I don't have a stylus, and I went to my office last night to get the stylus, and Philly Hall is locked down tighter than a drum. So I'm going to try again, but it looks like we're at like stage 4 lockdown, and I think that means you better have a reason better than missing the stylus to get in. So what we're going to do today is we're going to go through the process of linear programming in the simple fashion, and we're going to follow the appendix that shows the graphical solution method or the graphical technique to come up with solutions. And then we're going to look at the more complex problem at the beginning of the chapter to understand how that could be put into Excel. So to give you some motivation, why are we doing this? Because there is some temptation to say, oh, linear programming is something for advanced farm management, not something that we need to do here. I would say that there's 2 reasons to do it. So number 1, if you are moving on to advanced farm management, having a background in linear programming and a little bit of Excel will go a long way. As a manager, it helps you solve complex problems. And in this case, really just a simple paradox. We're trying to maximize profit producing corn and soybeans when corn has higher profit per acre, and overall, just planting corn is not the profit maximizing solution. And that kind of dovetails into the second reason. If you're a non-ag econ or ag business major, and this is kind of foreign to you, not something that you think you're going to do, it gives you an understanding of how a framework or a process can help you solve a problem that you otherwise would not be able to solve. Now, these problems are simple enough that you probably could get there through a guess and check fashion, but what you would probably be doing is basically the graphical solution technique, just in a roundabout way. So it's probably better just to do it in a more straightforward manner. So the steps in linear programming are as follows. Number 1, define the decision variables. Number 2, state the objective function. In terms of the decision variables. So we are now going to linearize the objective function. Number 3, state the constraints. In terms of the decision variables. And number 4, now, solve graphically has some sub-steps, but as you can see, we've run out of board. So we'll talk about number 4 when we get there. So number 1, define the decision variables. Variables are things that you can change or things that do change. They're not constant like a coefficient. And the variables are things that we can change in this problem, the appendix, are acres of corn and acres of soybeans that we plant. So C represents corn, S represents soybeans. The second, state the objective function in terms of the decision variables. We want to maximize 120C plus 96S. This is a profit maximization problem. Linear programming problems typically fall into one of 2 categories at this level for sure. We're either trying to maximize profit or we're trying to minimize cost, which in a roundabout way is maximizing profit, which is what we know firms try to do. So if we look at this max 120C plus 96S, we can have some sort of deep understanding of the problem before we go on and not just a memorization of steps. Every time we plant an acre of corn, 120 times 1, we make $120 of profit, which came from the enterprise budget. The enterprise budget is telling us at 150 bushels per acre and $4 per bushel, we have $600 of revenue and perhaps $480 of expenses, and so we have $120 of profit. And every time we plant an acre of soybeans, we have $96 of profit or profit contribution. So we could just start plugging numbers in here. Say, all right, well, what would happen if we planted 10 acres of corn and 10 acres of soybeans? Well, we'd have $1,200 of profit from corn and $960 of profit from soybeans. So we have, $2,100 of profit. Can we do better than that? Can we plant 15 acres of corn and 15 acres of soybeans? Sure. We can do that when we're just kind of messing around saying plant 10, 15 acres, knowing that we have 120 acres and we really have resources that align with using all 120 acres. But I know that I can do better than a couple of $1,000s of profit just simply by planting more. But I don't know, should I just plant corn, should I just plant beans, or should I plant some combination of the two? So write these down because I'm going to erase. Number 3 is state the constraints in terms of the decision variables. Now, the first constraint is so easy, it actually causes students difficulty once in a while. The first constraint is our land constraint. Every time we plant an acre of corn, we use 1 acre of soybeans. And every time we plant an acre, back that up. Every time we plant an acre of corn, we use 1 acre of ground. I think I said something goofy. And every time we plant 1 acre of soybeans, because remember that's what S is, we use 1 acre of ground. And together, this must be less than 120 total acres. Now it seems kind of funny and it's so obvious. If I plant an acre of corn, of course I'm going to use an acre of ground. But think about some other things that might happen that don't seem too far-fetched. Every time you plant an acre of corn, you need to have 1/10 of an acre of buffer. So maybe every time you plant an acre of corn, you use 1.1 acres of ground. Something like that could happen as well. But nonetheless, number of acres of corn plus the number of acres of soybeans have to be less than 120 because that's all we have. Can we plant 200 acres of corn? Absolutely not. Okay? So we would call that our corn constraint. Our second constraint is labor. Every time we plant an acre of corn, we use 5 hours of labor. And every time we plant an acre of soybeans, we use 3 hours of labor. And we have 500 hours of labor available. Okay? This is not saying that corn is less profitable because you use more labor. And when we look at capital, it's not saying corn is less profitable because we have more input requirements from a capital standpoint. It's just saying it is more labor intense. And if we're thinking that the enterprise budgets are economic budgets, which they are, the profitability of corn is absolutely higher than soybeans. But it doesn't change the fact that we may be constrained by the fact that it takes longer to plant and look after corn than it does for soybeans in this example. So we could call that our labor constraint. And finally, our last constraint is operating capital. Every time we plant an acre of corn, we need $200 to buy seed and fuel and fertilizer and so on, and pay labor. And every time we plant an acre of soybeans, we use $160, and we have $30,000 available. So this is my labor constraint, This would be my capital constraint. So now I have 3 constraints and 2 unknowns, and we're ready to move to number 4, solve graphically. Now I am going to recreate what's in the book, and then we'll solve. Okay. I'm going to try to do this very carefully and just one constraint at a time, because the graph gets busy very, very quickly. Okay? So, if this represents acres of corn and this represents acres of soybeans, the first constraint that makes the most sense to model is our land constraint. Now, graph paper works much, much better than measuring out marker lengths, but this will get us close. If we only planted corn and land was our only constraint, we could plant 120 acres of corn. That's what this point represents. 0 acres of soybeans, 120 acres of corn. And if we only planted soybeans, we could plant 120 acres of soybeans and 0 acres of corn. Or any linear combination between them. And of course, the trade-off of this is 1-to-1. Every time I give up an acre of corn, I get an acre of soybeans in return. And what I like to do is get rid of or shade the area of the graph that isn't feasible. And this is a word that is very common in management science, but we don't see it show up in the textbook, I don't believe. We are trying to define the feasible region of our graph. That's the area or the places that are not constrained by our resources. This is just showing, hey, you can't plant more than 120 acres. Everything past my land constraint is more than 120 acres. Okay? So I usually try to have some indication of what the constraints are, especially when they start to become numerous. Our second constraint, labor, was 5C plus 3S has to be less than or equal to 500. So, if we use all 500 hours of labor to plant corn, we could plant 90 acres of corn. Okay, so follow me here. 5C plus 3S is less than or equal to 500 is a line. The less than just allows us to talk about this feasible region and shading. If I use all of my capital to plant corn, I can plant 100, or not my capital, all my labor, I can plant 100 acres. And if I use all of my labor to plant soybeans, 500 divided by 3, oh goodness, it's 167, and 167 is about here, or any combination in between. Now, this part of the feasible region this part of the graph was already taken care of. However, this goes away. So what this is basically saying is you cannot plant more than 100 acres of corn. If you try to use all of your resources to plant corn, you're going to run out at 100 acres. You've only got enough labor to plant 100 acres. And this is the first place where we can start to understand why planting some soybeans makes some sense. As I'm moving along this curve, as I give up 5 hours of labor to plant corn, I have 5 hours of labor to plant soybeans. So if it takes 3 hours to plant soybeans and I've got extra ground, because I do, I can now plant 1 2/3 acres of soybeans for every 1 acre of corn that I give up. And 1.67 times 96 is more than $120. So as I'm moving along this line, I'm trading off 1 acre of corn for 1 2/3 acres of soybeans, which gives me more profit. So I certainly would go at least until this point. I can't continue on because past this point, I'm using more than 120 acres. And if I'm going this way, now my trade-off is 1 to 1. Now I give up an acre of corn, I only get 1 acre of soybeans in return, and I lose $24, $120 of profit contribution for 96. So if this were it, if the problem were done right here, we would solve these two equations and say, what's that point? That's my profit maximizing point for sure. But it's not. I have one more constraint left, and that is my capital constraint. And the capital constraint says 200C plus 160S has to be less than or equal to 30,000. So if I only plant corn, my corn intercept is way up here. It's 150 acres of corn. If I use all of my money to plant corn, I got enough money to plant 150 acres. Even though I don't have enough labor, even though I don't have enough land, that's what this point is telling me. I'm only thinking about capital. And if I use all of my money to plant soybeans, 30,000 divided by 160 is 183, I think. That's way over here. So my capital constraint is over here in an area, this one, that we already know we can't plant. It's more ground than we have available. This is just saying you have a line of credit or you have a savings account or you have cash reserves from last year's profits that's large enough to plant far more than what you have. This is what's called a non-binding constraint. And it actually has some importance. You might think, okay, well, why would we even bother with this? We could say that's what it is. We have plenty of money. It could be that it's close to becoming a binding constraint. If it were closer to here, it might be something that would make the operator or the manager consider, hey, do we have enough money next year to plant? It might be the thing that causes you to call your banker and say that you need a larger line of credit. Okay, so what we're left with here is this smaller feasible region. I know this is my profit maximizing point. The graphical solution technique says take your objective function and move it outward until you're barely touching any longer. Or I like to think about, okay, this was a spot that made some sense. 100 acres of corn. 100 acres of corn produces 100 times 120, $12,000 of profit contribution. Are we going to make more money if we produce there? And likewise, 120 acres of soybeans, 120 times 96, we can see if we can beat that. I'll plug it into my computer quickly. $11,520. So if we only had the choice between should we plant all corn or all soybeans, clearly it's all corn. So our goal is, can we make more than $12,000? And I'm suggesting that at this point, where my first two constraints cross each other, we will make more than $12,000. Okay, to do this, how do we erase the graph? So go to your textbook, and you can look at that graph. And the two constraints that are binding, 1C plus 1C plus 1S has to be less than or equal to 120. And our labor constraint, 5C plus 3S has to be less than or equal to 500, were the two lines that we're crossing at our extreme point. That's another one of those management scientist words. That's where the two lines cross, and where I'm suggesting is the profit maximizing location. So all we have to do is solve these two equations, two unknowns. We can do that. And this one's set up really nicely for us because I can solve this one for S or C and substitute it into here. So 1S is equal to negative 1C plus 120. So if I plug this wherever I see an S, I can get an answer. 5C plus 3 times negative C plus 120 is equal to 500. So 5C minus 3C plus 360 is equal to 500. So 2C is equal to 140, which means that C is equal to 70. And if I plug that back in here, S is equal to 50. Or if I plug it back in here, 5 times 70 is 350. So 350 plus 3S is equal to 500. If I subtract 350 from both sides, 3S is equal to 150. S indeed is equal to 50. So my profit maximizing solution, corn 70 acres, soybeans 50 acres, can be plugged into my objective function, which was to maximize 120C plus 96S. Well, 120 times 70 is $8,400 plus 96 times 50 is $4,800. 4,800 plus 8,400, my profit is equal to $13,200, which is a fair bit more than $12,000. So this should give you an idea how, if you continue on with management science, you could make $1 million. All right, so that is the graphical solution technique. And the last thing that I said I would do is go over the linear programming tableau and talk it over. And I will do that very quickly because this is a long time to be watching this. So if you get to table 11.2, first we're looking at technical coefficients and then estimating gross margins. And this is a more detailed look at what a problem would be that you would need Excel for. So my decision variables in this case, and when we have this class face-to-face, one of the exam questions, I take this exact question and say, here's everything that I just put it into a paragraph and say, how many decision variables are there? Well, the decision variables are how many acres of cotton are you going to plant on Class A cropland? How many acres of soybeans are you going to plant on Class A cropland? How many acres of corn are you going to plant on Class A cropland? How many acres of soybeans are you going to plant on Class A B cropland? And how many acres of corn you are going to plant on Class B cropland? But wait, there's more. You are also going to determine how many beef cows and stocker steers you are going to raise. And that's where we can see, hey, I'm not just looking at how am I going to split up land. Now I'm also looking at how am I going to split up that capital and how am I going to split up labor. So when you look at Class A cropland, there is a Class A cropland constraint. 1C plus 1S plus 1CO has to be less than or equal to 520. And notice there are dashes for Class B soybeans and Class B corn because that's not Class A grain. That's Class B. Then I have a Class B constraint. Notice I have dashes because Class A cotton and Class A corn aren't the same as Class B cotton and Class B corn. And this is just saying, well, every time I plant an acre of soybeans on my poor ground, I use up an acre. And every time I plant corn, I use up an acre. But it's two different constraints. I'm saying I have this ground that's Class A and this ground that's Class B, or I have this ground that's irrigated and this ground that's not irrigated. Might be a better solution to this. But then I also have a pasture constraint. It's saying, hey, beef cows and stocker steers, they're going to utilize pasture, and it looks like for each one they require 2 acres. So I only have 380 available. So at most, I could have 190 beef cows or 190 stocker steers. So this is, again, just showing how we can put a lot of different resource constraints into one problem. Labor, all of them are competing. Operating capital, all of them are competing. All we do then is we put this into Excel in exactly the same format that we did for our simple problem, and Excel spits out the solution. Now, the corn and soybeans, when there's just 2 decision variables, pretty easy. You can do that by hand. You could do it just thinking out loud and figuring it out. But this one you sure couldn't. It would be much, much more difficult. Okay, that is plenty. 27 minutes of me is 26 more than a lot of you probably wanted to hear. But I hope it's helpful, and hopefully I'll see you on Zoom tomorrow.